Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges and my courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, IIT-Jam, Jest, Tifr and other exams related to physical science. Okay, so this is the so we are going to I'm going to solve the December 2019 PYQ today onward, as I have already completed uh, CSIR net physics PYQ of June 2019, and I have completed that in 11 lectures. Okay, so today onward I'm going to solve the physics PYQ of December 2019. Okay, so this is the first part of the series for the PYQs of December 2019. Okay, so I'm going to start. And before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes, which are going to help you to crack the exams related to physical science. Okay, so I'll start the question now. Question number first. Question number first is, these are part B questions. Okay. Question number first is, the angular frequency the angular frequency the angular frequency of angular frequency of oscillation of quantum harmonic oscillator angular frequency of oscillation of quantum harmonic oscillator quantum harmonic oscillator quantum harmonic oscillator in two dimensions in two dimensions is omega if it is in contact with if it is in contact with if it is in contact with an external heat bath and an external heat bath at temperature T at temperature T. its partition function its partition function its partition function is okay. In the following in the following in the following beta equal to 1 upon kt kbt, right? K is Boltzmann constant, and options are, option number A is e to the power 2 beta h cut omega upon 1 minus, e to the power, my apologies, this is e to the power 2 beta h cut omega minus 1 whole square. Okay, and option B is e to the power beta h cut, e to the power beta h cut, omega upon e to the power beta h cut omega minus 1 whole square. Okay, option C is e to the power beta h cut omega, e to the power beta h cut omega upon e to the power beta h cut omega minus 1, e to the power beta h cut omega minus 1, and option D is e to the power 2 beta h cut omega, 2 beta h cut omega upon e to the power 2 beta h cut omega, 2 beta h cut omega minus 1. Okay, so this is the question. I'll solve it. Meanwhile, let me just check the sound. Okay, option number E is yes, I'm audible. Okay, so I'm going to proceed now. So the question is, the angular frequency of oscillation of quantum harmonic oscillator in 2 dimensions is omega. Okay, so angular frequency of quantum harmonic oscillator is given, which is omega, if it is in contact with an external heat bath. Okay, it is in contact with external heat bath. Okay, at temperature T, its partition function you need to find out, where beta equal to 1 upon 80, and these are the options which is given. Okay, so I'll solve it now. First we will find the energy of harmonic oscillator in 2D. Okay, so energy of harmonic oscillator. Okay, energy of harmonic oscillator. Okay, that is E is going to be n plus 1 h cut omega. Okay, this is the energy in 2D. Okay, okay, and where n is nx plus ny. Okay, nx plus ny, right, and in 2D, so it is in 2D, in 2D. Okay, so now we'll find the partition function. Partition function is, we know that is right, z equal to sigma I gi e to the power minus beta ei, right? That's what we know. This is the partition function, guys. Okay, this is the partition function. Okay, now and this is the part. So for this case, the partition function is going to be sigma n equal to 0 to infinity n plus 1, which is starting with 0, okay, for harmonic oscillator, e to the power minus this one, beta n plus 1 h cut omega, beta ei, right? This is the partition function, and here degeneracy is degeneracy for a quantum harmonic oscillator is n plus 1, okay. So this is n plus 1, guys, okay. So gi e to the power minus beta n plus 1 h cut omega. Now very simple, we'll open it. So it is going to be uh, z equal to, we'll put n equal to 0, so it is going to be e to the power minus beta h cut omega. Now n equal to 1, so 2 e to the power minus 2 beta h cut omega plus 3 e to the power minus 3 beta h cut omega, okay, plus so on. Okay, guys, right. Now we'll simplify it further. So that is going to be here. There's a formula for it, right? So this for this formula, this is going to be it is going to be e to the power minus beta h cut omega upon 1 minus e to the power minus beta h cut omega, okay, plus e to the power minus 2 beta h cut omega upon 1 minus e to the power minus beta h cut omega whole square, okay. So this is going to be this. I'll tell you the formula. So there's a formula, okay. Okay, so formula is if you have like this, e to the power x plus 2 e to the power 2x plus 3 e to the power 3x plus 4 e to the power 4x plus so on, okay. If you have this type of expression, the direct formula for this is okay, so this is going to be equal to e to the power x upon 1 minus e to the power x, oh sorry, yeah, 1 minus e to the power x plus this one, e to the power 2x upon 1 minus e to the power x whole square, okay. This is the formula, guys, which I have used here. So here this is e to the power minus beta h cut omega, so consider this is x, okay, plus e to the power minus 2 beta h cut omega 3, like this one, right? And this formula is going to be e to the power x, this is e to the power minus beta h cut omega upon 1 minus e to the power beta h cut omega plus e to the power this one, e to the power 2x upon 1 minus e to the power x whole square, right? So e to the power minus 2 beta h cut omega upon 1 minus e to the power beta h cut omega whole square, okay. So I have used this formula. Now I will simplify it further. So this is going to be that z is going to be so we'll take LCM here, right? LCM. So this is going to be 1 minus e to the power minus beta h cut omega whole square will be a here. Okay, we'll solve it and then we'll simplify it, right? So this is going to be e to the power minus beta h cut omega, this one, okay, e to the power minus beta h cut omega into 1 minus into 1 minus e to the power minus beta h cut omega, okay, beta h cut omega, and this is plus e to the power minus 2 beta h cut omega, okay. We have just simplified this one, okay. So LCM is this, right? And then it is going to be z equal to 1 minus e to the power uh, minus beta h cut omega whole square, and this is going to be, we'll multiply this right with this, so it is going to be e to the power minus beta h cut omega, e to the power minus beta h cut omega, e to the power minus beta h cut omega minus, this will multiply this, right, e to the power minus 2 beta h cut omega, e to the power minus 2 beta h cut omega plus this one, e to the power minus 2 beta h cut, e to the power minus 2 beta h cut omega, right? This and this will get cancelled, okay. So that is going to be e to the power minus beta h cut omega upon 1 minus e to the power minus beta h cut omega whole square, right? So now what we are going to do, we'll take e to the power of beta h cut omega common, okay. So it is in square, right? So so this is going to be, here we'll take e to the power minus 2 beta h cut omega common because it is in square, right? So it is 2, and this is going to be e to the power uh, uh, e to the power beta h cut omega minus 1, okay, and this is upon e to the power minus beta h cut omega, this is the one, right? So now this will go up in the numerator, and this sign will be plus, and this will get subtracted, and then this value is going to be e to the power beta h cut omega upon e to the power beta h cut omega minus 1, okay, this one. So this is the answer, guys. So which option is matching? E to the power beta h cut omega, e to the power beta h cut omega upon e to the power beta h cut omega minus 1 whole square. So option B is matching, guys. E to the power beta h cut omega upon e to the power beta h cut omega minus 1 whole square, okay. So this is the answer, guys, okay. A very good question, guys. It's part B question. Next question we are going to solve. Question number 2. Question number 2, okay. Question number 2, and this is also a good question, and this is related to percentage error question, okay. Very simple question. A student measures student measures the displacement x, the displacement measures the displacement x from the equilibrium from the equilibrium of a stressed spring stretched equilibrium of a stressed spring, and so the student measures the displacement from the equilibrium of stressed spring, okay, and reports it be 100 micrometer, 100 micrometer with a 1% error. Okay, so 1% error. So error is 1%. With a 1% error, 1% error, the spring constant K, the spring constant, the spring constant K is known to be K is known to be K is known to be 10n upon m with, that is 10 Newton per meter. Okay, 10 Newton per meter with 0.5% error. Okay, 0.5% error, 0.5% error. The percentage error, the percentage error, the percentage error in the estimate of, in the percentage error in the estimate of, estimate of, in the estimate of the potential energy, the potential, the potential energy, the potential energy V equal to kx square, half kx square is. Okay, options are given. Option number A is 0.8%, option B is 2.5%, option C is 1.5%, and option D is 3%, 3.0%. Okay, so this is the question. A student measures the displacement x from the equilibrium of a stressed spring and reports it to be 100 micrometer with 1% error. Okay, the spring constant K is known to be 10 Newton per meter with 0.5% error. Okay, so these are the error. The percentage error in the estimate of the potential energy. So the estimate error in the potential energy, that is V equal to half kx square, we need to find out. Okay, first of all, it's a very good question and very simple question. First of all, you should know what the formula for percentage error. Okay, the formula for percentage error is error is estimate value, approximated value. Okay, approximated value minus approximated value minus actual value upon actual value into 100. Okay, so this is the percentage error formula, guys. Okay, so we have to solve this now. We have to solve this now. Okay, so error is given. Okay, so what error is given? Error, that is percentage error in this one, stressed spring. Okay, the reports this with percentage with 1% error. Okay, so error means error in displacement. Okay, so that is from this formula, error in, that is delta x upon x. Okay, that is this one, delta x upon x into 100. Okay, or we can write delta x upon x percentage equal to given 1%. Okay, and delta k upon k, that is in spring constant. Okay, k upon k into 100, or delta K upon K percentage is given, that is 0.5%. Okay, this is given, guys. This is given. This is given. Okay, so now we have to find out the percentage error, okay, of potential energy. So we have been given V equal to half kx square. So we'll take ln on both sides. Okay, ln on both sides. So this is going to be ln v equal to ln half plus ln k plus ln x square. Okay, so this is going to be ln v equal to, we have taken ln, okay, log ln v is going to be, this value will be 0, ln half, so this is ln k, or we can write it, okay, ln half plus ln k plus, with log property, ln x square is 2 log x, right? 2 ln x, so this is 2 ln x, right? Now we'll differentiate this. Okay, so this is going to be differentiating with respect to, so del v upon v is going to be equal to 0 plus this one, this is 0. Okay, so this is going to be this one ln k, that is del k upon k del k upon k, okay, plus 2 del x upon x. We have differentiated with respect to, we have differentiated it, okay, both left hand side and right hand side. Now first for percentage, we'll do del v upon v into 100 equal to del k upon k into 100 plus for percentage, okay, 2 delta x upon x into 100. This value is percentage, right? So del v upon v percentage is going to be this value we have been given, okay, del k upon k percentage plus 2 del x upon x percentage. This percentage error is given, right? This percentage error is given. Del x is 1% and this is del k upon k is 0.5%. Okay, this value. So we'll just put the value. So del v upon v percentage is going to be, this is going to be this value is del k, this is 0.5, right? Del k upon del is 0.5%, 0.5% plus this is 2 into 1%, right? And this is going to be 2.5%. Okay, so percentage error in okay, so this is percentage error in the estimate of potential energy, right? Potential the percentage error in the estimate of potential energy and potential energy is this, okay, 2.5 is the answer. So which option is matching? This one. This is how we solve it. Okay, so 2.5 is the answer. So which option is matching? 2.5 means option B is the correct option. Okay, option B is the correct option. Okay, next question, guys. Next question. It is also a very good question, guys. Question is question third. Question third is the Hamiltonian of the Hamiltonian of two interacting particles, two interacting Hamiltonian of two interacting particles, two interacting particles, okay, one with spin half, spin 1, and other with second one, okay, other with spin half, other with spin half is given by is given by is given by h equal to a s1 dot s2, okay, plus b s1x s1x plus s2x, okay, s1x plus s2x, where s1 and s2 denotes s1 and s2 denote s1 and s2 denote the spin operator, the spin operators spin operators of the first and second particles, of the first and second particles, first and second particles respectively, and A and B are positive constants, positive constant constants, positive constants. The largest eigenvalue, the largest eigenvalue, eigenvalue of this Hamiltonian is of this Hamiltonian is Hamiltonian of this Hamiltonian is, okay. Options are, option A is 1 by 2 a h cut square, a 1 by 2 a h cut square plus 3 b h cut. Option B is 3 a h cut square, 3 a h cut square plus 3 h cut, sorry, b h cut, okay, this is b h cut, b h cut. Option C is half 3 a h cut square, 3 a h cut square plus beta h cut. Option D is option D is a h cut square, a h cut square plus 3b h cut, okay. So this is the question, guys. Okay, question is the Hamiltonian of two interacting particles with one with spin 1 and the other with spin half is given by this, okay, where s1 s2 denote the spin operators of the first and second particles respectively. A, B are constant, positive constant. The largest value of this Hamiltonian is the largest eigenvalue of this Hamiltonian, and h is given. This is That is A S1 dot S2 plus B S1x plus S2x. Okay, so we are going to solve it now. Okay, so this is going to be, so since we have been given H Hamiltonian for these two particles, A S1 dot S2, these are spin operators, plus B S1x S1x plus S2x. Okay, S2x. Okay, this one. So since we know mod S square is mod S1 square plus mod S2 square minus plus 2 S1 S1 dot S2, right? S1 dot S2, this we know. This implies value of S1 dot S2 is going to be mod S square minus S1 square mod S1 square minus mod S2 square, okay, upon 2, right? So we'll put the value here. So H is going to be A into mod S square minus mod S1 square minus mod S2 square. Okay, this one upon 2 plus B into S1x plus S2x. Okay, now we have, so now we have given spin, right? Spin is given. We have given S1 is given. For first particle spin is 1, for second particle S2 the spin is half. This is given, right? So S is going to be 3 by 2 comma half, right? Total angular, total spin, right? So 3 by 2 comma half. 3 by 2 comma half, because this is 1, right? So this is value is S1 plus S2, value of S is S1 plus S2 comma S1 minus S2. Okay, these are the value for S. We know we have done this in atomic physics, right? So these are the value S value. Now we have to, so from here S1 S2 is given. From here we can find out operator S. Operator S is going to be, operator S square is going to be S into S plus, sorry, my apology. So this is going to be S into S plus 1, S into S plus 1, H cut square, right? Similarly, operator S1 is S1 square is going to be S1 into S1 plus 1 H cut square, and similarly S2 square is going to be H cut square S2 plus, sorry, this is H cut square S2 into S2 plus 1. Okay, these are the values, and we have to find out the largest eigenvalue. Okay, largest eigenvalue of Hamiltonian. So for largest eigenvalue of H, will take the largest value of S, that is, will take S equal to 3 by 2. So we have two values, right? S 3 by 2, and so we'll take largest value for getting largest value of H. Okay. Okay. So So now we'll put the value. Okay, so Hamiltonian is going to be, we'll put value here in equation. You can say this is equation 1. Okay, here we'll put the value. And also here guys, I would like to tell you here, the value of Sx, S1x is, spin is 1, right? So S1x value is going to be h cut, since spin is 1, and the value of S2x is going to be h cut by 2 because spin is half. Okay, so this is the values of S1 S2. So we'll put the value in equation 1. Okay, this equation. So h is going to be a into S1 plus. So I think it is better to write to get the value S1 S2 S1 mod square this. Okay, we can write it. So S value is 3 by 2 plus 1 h cut square, right? This is the s square here, this one, minus mod s1 square is, this is the value is for s1 spin is 1, right? Spin is 1, so 1 into 1 plus 1 h cut square minus mod s this one mod s2 square, this is the value of s2 is half into half plus 1 h cut square, and then plus b, this one plus b s1x and s2x. So this is going to be uh, h cut plus 1 by 2 h cut, right? Upon, is there upon? Yeah, not upon. Okay, so this is going to be, for this is upon. Okay, for this value upon 2. Okay, so we'll proceed further. So h is going to be, we'll calculate this. This is 3 by 2 plus 1 5 by 2, that is 5 3s are 15. So a into 15 h cut square by 2 minus this is 2 h cut square, and this is 1 by 2, this is 3 by 2, 3 by 4, 3 by 4 h cut square upon 2 plus b, this is going to be 3 h cut by 2, right? So we'll solve this. So value of h is going to be, so this is, we'll take LCM, right? So this is going to be 4, and this is a into 15, this is a h cut square will take common, so if 15 is going to be 15 minus 11. Okay, so this is 11 upon 8 plus b 3 h cut upon 2, right? 3 h cut upon 2. Okay, so we'll now simplify it further. We'll simplify it further. So this is going to be, h is going to be, so here this is going to be 4 will cancel 8 by 2 times, right? So this is going to be, so, and 1 by 2 will take common. Okay, so this is going to be 1 by 2 we have taken common, and this is going to be a h cut square plus 3 b h cut, right? This one a h cut square 3 b h cut. Okay, 3 h cut. So this is the answer. So which option is matching, guys? Let me check which option is matching. Option number A is matching, guys. Option number A. So this is the option number A. This one. Okay. This one is the correct. 1 by 2 a h cut square plus 3b h cut. 1 by 2 a h cut square plus 3b h cut. Okay. So this is the correct answer, guys. Very good question. I would request you to practice these questions. Okay. Very important questions. I'm solving for you. Next. Question number 4. This is also very good question. Question number 4 is, consider the set of polynomial. Consider the set of polynomials. Consider the set of polynomials. Set of polynomials. Okay, set of polynomials, which is x equal to x, which is function of t equal to a naught plus a1t plus a2t square plus so on an minus 1 t to the power n minus 1. Okay, so this is the set. Consider the set of polynomial xt equal to a1 a naught a1t a2t so on an minus 1 t to the power n minus 1. Okay, this is the set of polynomial in t of degree. Polynomial which is in t, right? In t of degree less than n. Okay, degree less than n, such that given x0 equal to 0 and x1 at 1 equal to 1, this set is, so this set is number A, constitutes a vector space of dimension n. Constitute vector space of dimension 1 Option B is constitute a vector space of dimension n minus 1. Constitute a vector space of dimension n minus 1. Similarly, option C is constitute a vector space of dimension n minus 2. Okay, and option D is does not constitute a vector space. Okay, does not constitute a vector space, does not constitute a vector space. Okay, so this is the question. Consider a set of polynomials. So this is set of polynomial in T, okay, of degree less than n, right? So such that x0 equal to 0, okay, x at 0 equal to 0 and x1 equal to 1. This is not. So this set constitute a vector space of dimension 1, constitute a vector space of dimension n minus 1, constitute vector space of dimension n minus 2, or doesn't constitute a vector space. Okay, well, so we'll solve now. Very good question. So we have been given the polynomial, right? We'll write that polynomial first. Okay, so this is xt is given. This is given a naught plus a1t A1t plus A2t plus so on a minus 1 t to the power n minus 1. Okay, so this is the polynomial given. Now we'll put the condition. First condition is at x0, at t equal to 0, x0 equal to 0, right? This is given. So if you put here, so this is going to be x0 equal to, at t with 0, this is going to be a0, right? Or a0 is going to be 0, right? This is one. Now second condition is xt equal to the same a0, second, then xt is going to be, because a0 is 0, right? So xt is going to be a1t plus a2t plus on a n minus 1 t n minus 1, because a is 0, right? For first condition, x0 equal to 0, so we put this in equation 1, right? In equation 1, so this is, then value of a0 is 0, then equation 1 becomes a1t plus a2t, a2t square plus so on, right? Now we know the condition for being vector space, right? That t square t cube so on t n minus 1 will make basis vector, okay, will make basis vector, okay, will make basis vector if P1, P2, P3 so on, will make basis vector if C1t plus C2 t square plus C3 t cube plus so on equal to 0, right? And 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 if C1 equal to C2 equal to C3 equal to so on equal to 0, these values should be 0, right? But according to question, this contradicts this equation 2, right? If you put this equation 2, right? Because if you put t equal to 1, okay, just wait, we haven't put the condition. So since here we have been given, I'll write, since we have been given this second condition, let me write. So here also we have been given this equation, right? This is x1 equal to 0. So we'll put x1 equal to 0. So there x1 equal to 1 given, x1 equal to 1 given, okay? According to question, x1 equal to 1 given, right? So if you put this in 2, so this is going to be x1, right? x1 is going to be 1 equal to a1 plus a2 plus a3 so on a n minus 1, okay? A n minus 1. This is the equation number 3, very important equation, okay? Because x1 will put t equal to 1 and t equal to 1 and x equal to 1, right? And t equal to 1 and xt equal to 1, right? So we have put this. This is the equation number 3, very important equation, guys. This one, okay? Very important equation. Well, so now C1, C2, C3 should be 0, right? But if you yeah, so means this value should be 0, right? But it contradicts with equation 3, because we can see a1, a2, a3, a3, this becomes 0, right? For this case, this, you can see for this case, if we check, so here t cube will make a basis vector if this equal to 0, right? And c1, c2, this must be 0, right? And if we take this condition here, right? But we can see C1 plus C2 plus C3 so on should be 0, right? So here we can say we can see A1 plus A2 plus A3 so on A n minus 1. This sum is not 0. This gives value 1, right? So this statement contradicts with this 3, equation 3, right? So it means it will not constitute a vector space. Okay. This implies will not constitute a vector space. Okay, so it will not constitute a vector space. It doesn't constitute a vector space. Okay, because this condition is not satisfying this, because here we can see if we add a1 plus a2 plus a3 so on a n minus 1, this value is 1, not 0. That should be 0, right? Okay, right. So if we take R, because here we have taken C1 C2, right? If we take same case here, right? A1 T1 plus A2 T2 plus A3 T A1 T A1 T plus A2 T square plus A3 T cube plus so on equal to 0, right? Then A1 A2 A3 AN, right? They are not going, they are not equal to 0, right? So this value, their sum is, we can see here 1, right? So it means it will not constitute a vector space. Okay, guys. So this is the equation, and so which option is matching? Option number, which option? Option D is matching, guys. Okay, so this option, okay, doesn't constitute a vector space. Okay, because we have got this from equation third. This equation. Next question, guys. Question number 5. Question number 5. Question number 5 is very simple question. Okay, formula based question. Consider black body radiation. Consider black body radiation. Consider black body radiation. Consider black body radiation in thermal equilibrium. In thermal equilibrium. Consider black body radiation in thermal equilibrium contained in a two-dimensional box. Contained in a 2D box. The dependence of the energy density of the energy density on the temperature temperature T is. Okay, options are option A T cube, option B T, option C T square, and option D T to the power 4. Okay, T to the power 4. So the consider black body radiation in thermal equilibrium contained in 2D box. Okay, so black body radiation is in 2D box. Okay, contained in 2D box, and it is in thermal equilibrium. Okay, the dependence of energy density on temperature you need to find out. Okay, so there is a formula for that. Okay, the energy density for energy density of black body radiation in 2D. Okay, this we know. There is a formula, guys. You need to note down and memorize. Okay. So there's a formula: energy density for 2D photon, energy density for 2D photon, 2D photon, energy density for 2D photon, right? U equal to 2 zeta, which is function of S, KT, K is the Boltzmann constant, right? KBT, right? KT square, cube to the power cube upon H cut C square pi. Okay, so this is the formula, guys. This is the formula where zeta S, his value is 1 plus 1 upon 2 square plus 1 upon 3 square plus so on. Okay, this is the value of zeta. This is called Riemann zeta function. Okay, Riemann zeta function. Okay, so energy density U is proportional to T cube, right? Or other are constants. So energy density U proportional to T cube, right? So you can note down this as well. The energy density is proportional to T cube if black body radiation is in the 2D box. Okay, so U proportional to T cube. Okay, so these two you need to note down, and T cube is the answer. So answer A is the correct answer. Okay, this is this one, T to the power cube, T to the power cube, T to the power cube. Option A is the correct one. Okay. Okay, next question. Next question is question number 6. This is also very good question and very simple question. The energy eigenvalue, the energy eigenvalue, energy eigenvalue, energy eigenvalues of a particle of a particle, energy eigenvalues of a particle of mass m, energy eigenvalues of a particle of mass m confined to a rigid a rigid a rigid one dimensional box, one dimensional rigid one dimensional box, dimensional box of width L, of width L, R En equal R En, okay, R En, okay, that is the energy eigenvalues. Okay, REN, where n equal to 1, 2, 3, so on. Okay, energy eigenvalue is En. Okay, REN. If the walls of the walls of the box are moved very slowly, are moved very slowly, towards each other, towards each other, towards each other, towards each other, the rate of change of the rate of the rate of change of time dependent energy, change of time dependent energy, rate of change of time dependent energy of the first excited stages of the first excited state is first excited state is option A is E2 upon L dl upon dt. Okay, option B is 2E2 upon L dl upon dt. Option C is minus 2 E2 upon L dl upon dt, and option D is minus E1 upon L dl upon dt. Okay, so this is the question. So we have been given the energy eigenvalues of a particle of mass m confined in a rigid one-dimensional box. Okay, so the particle is one-dimensional box which is rigid. Okay, of width L is the width. Okay, and energy eigenvalue is En, right? If the wall of the box are moved very slowly towards each other. Okay, so we have moved the walls of the box towards each other very slowly. The state of the change, the rate of the change, rate of the change, rate of the change of time dependent, rate of the change of time independent energy, time dependent energy of the first excited state you need to find out. Okay, so very simple question. So we need to find out this. For first excited state means dE2 upon dt we need to find out. Okay? For first ground state E1, energy is E1. For first excited state it's E2. So this we need to find out. So we know the energy En, right? Energy En is n pi square h square upon 2 ml square for 1D box, right? So for first excited state, that is E2 is going to be 4 h square, n is 2, right? N square 4 h square pi square upon 2 ma square, right? Now we'll differentiate it with respect to T d2 upon dt, that is going to be minus L square, right? L and T L. So in this case, this is going to be L square. L square. So this is going to be L square, right? So del upon dt. So right. So these are constant. Only L is there, right? So this is going to be minus 2 because L will go up, right? So minus 2 d upon d L cube d upon dt L cube, right? D upon dl L cube, right? Minus L minus d upon dl L to the power minus 2, right? Minus 2 because we know how to differentiate it, right? So this is minus 2 4 pi square h square will remain as it is upon 2 ml square 2 ml cube it will be, right? 2 ml cube, then dl upon de2 upon dl upon dt, right? dl upon dt. Very simple, right? But we have done is this one, d upon dt into L to the power minus 2. So this is going to be minus 2 into L to the power n 3 into dl upon dt, right? That's what we have done, and this is the constant. Okay, this is L cube, right? It will go there. Very simple differentiation. 2 will get cancelled. Okay, so this is going to be uh, or we can write it like this. Will not cancel it, and this value is going, this value is E2, right? E2. So dE2 upon dt is going to be E2, right? And dl upon dt. This is the answer. Change in rate of change of time dependent energy of first excited state. The answer is this one. 2 upon L E2 dl upon dt. Which option is matching? 2 upon minus 2 upon L E2 dl upon dt. Right? So option C is matching, right? Option C. This minus 2 E2 upon L minus 2 E2 upon L dl upon dt. dl upon dt. Right? Option C is the correct option. Very simple question and done. Okay. Well, now there is one more question. Time is already over. Okay, guys. So I'm going to stop here, right? Remaining question we'll do in next class. Okay. Is there any issues? Let me check. Yes, camera is not working, right? There is some issue. Okay, guys, now it's working. So there is one more question remaining. Okay, guys. Okay, guys. So I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes, right? Which are going to help you to crack the examinations related to physical science. Okay. Okay, guys. So thank you so much for watching my video, and remaining questions we are going to do in next class. And thank you so much. Bye now.